All right, so um, again, I'd encourage you to break this stuff up if you can. We're going to talk some about magnetic flux, and then there's 5 examples that follow which correspond to these 4 points. So maybe consider taking a break between each of the 4 points here and letting things digest a little bit. These 5 examples will show you how Faraday's law is applied in a variety of situations. So let's talk a little bit about magnetic flux, since that's an important part of Faraday's law. Phi b for magnetic flux, integral of b dot dA. This is not a closed integral. It's not a closed surface. This is going to be an open surface, similar to Gauss's law, but an open surface. Dot product, of course, cosine theta b dA. When you integrate here, you are integrating things that depend on the area, ultimately. Okay? So if something changes with time, but it doesn't depend on the area, it comes out. If the magnetic field was changing with time, but the magnetic field was uniform over the entire area, it can come out. If the angle is constant, it could come out. If the angle changed with time, it could come out. As long as the angle doesn't have to do with the area. So, as long as the magnetic field doesn't change its angle across the entire area, that would be constant. If the magnetic field somehow changed its angle throughout the area, this could not come out. So there's 4 ways that you could change the flux here. You can change theta, which is the angle between B and A. And remember, A is perpendicular to the area itself. So theta here, if theta is 0, the flux gets maximized. If theta is 90, no flux. Another way that you could change the amount of flux is to change the magnetic field strength. You could put more B field lines through here, or you could get rid of some of these and have less. That would change the flux. Another way to change flux is change the size of the area. So if you took this loop and you made it bigger, or you shrunk this loop down and made it smaller, that would change the flux. And lastly, if you had a loop like this, if you moved it outside, so it was over here, and only half of the loop stuck into the magnetic field, that would also change the flux. So the next 5 examples correspond to those 4 categories. So number 1 was changing the angle. That's going to be example 1. Here we've got a loop which starts perpendicular to the field, and then it starts rotating starts rotating over time, right? And omega here is an angular speed, which is in radians per second. So if you take radians per second and multiply it by seconds, you will get radians. So the angle that the loop has rotated through is omega t. This is like angular kinematics again. And at time 0, theta is 0, and then it starts rotating. I'm just going to call this direction positive. So what do we need to do here? When we look at the integrals here in Faraday's law, this part is not useful. What is our goal here? Find the EMF, electromotive force, that's voltage. Find the voltage in the loop as a function of time. So this is voltage, and this is flux. And we don't know anything about the electric field, so we don't need that here. So negative d phi b dt. What is the flux? Well, flux was the integral of the magnetic field times the area. And of course, this is a dot product, so it's going to be cosine theta. I'll add in my vector signs there. So b dA cosine theta. Now, b is constant, it comes out. Cosine of theta is not constant, it changes with time, but at any given moment in time, the magnetic field is at the same angle to the loop. At any moment in time, the magnetic field is always at the same angle. So at time 0, the magnetic field is always perpendicular to the loop. At some later time, the magnetic field might always be at 30 degrees. So that can come out. And then the integral of dA is just going to be the area of the loop area. And in this case, we have a circle, right? So just plug everything in. It's the time derivative of BA cosine omega t. Right, and theta was omega t. We established that up there. When you take the derivative of cosine, it's negative sine. Negative and negative will cancel out. BA omega sine omega t. I'm going to stop this one now, and I'll make a new video for the next 2 examples. The next 2 examples are going to cover the change in the field strength, and then there'll be perhaps one more video each for each of those.